Title of the module: Composition of Functions and Invertible Functions. In this session, we are going to learn about the concept of inverse of a function, composition of functions, and equality of functions. We also will get to know how to find the inverse of a function and the numerous results linked to these specific topics. Suppose we have a function f that takes x to y so that f of x is equal to y. An inverse function which we call f inverse is another function that takes y back to x. So, f inverse of y is equal to x. For f inverse to be an inverse of f, this needs to work for every x that f acts upon. The inverse of a function. A function f from a to b has an inverse if and only if the set obtained by reversing the ordered pairs of f is a function b to a. If f from a to b has an inverse, the function f inverse is the collection of all elements b comma a such that the ordered pair a comma b belongs to f, and this is called the inverse of f. We shall now try to understand the inverse of a function better with the help of some examples. Now, we have already seen that the inverse of a function is beginning from a function itself. So, if we have a function f from a to b, f inverse is going from b to a. So, that is what we have represented here. So, f inverse is a collection of ordered pairs b comma a such that a comma b belongs to f. The purpose of writing this in ordered pairs is that if a comma b belongs to f implies that f of a is equal to b, right? And f inverse is a collection of ordered pairs b comma a such that a comma b belongs to f means that f inverse of b is equal to a. So, that is the meaning of this ordered pair that we have represented here. Now, if you can see this example, we have a domain A and a codomain B, and we have elements A, B, C and D on A and 1, 2, 3 and 4 in the codomain set B. Now, there is some sort of mapping here. So, as you can see from the picture, A has been mapped onto 2, D has been mapped onto 1, B onto 4, C onto 3. Is it a function? Yes, it is a function. We do not see any mappings of one element onto two elements, and also there are no elements which are unmapped here. So, this is clearly an example of a function. Now, f inverse is merely reversing the position. So, f is from a to b means that f inverse goes from b to a. So, what was the codomain here becomes the domain in f inverse, and what was the domain for f becomes the codomain in the case of f inverse. So, 1, 2, 3 and 4, A, B, C and D, the mappings are not disturbed at all. For example, A goes to 2 here means that 2 goes to A in this mapping. If C is going to 3 here, then automatically 3 should have been mapped to C. So, this is how f inverse works. So, I hope that made the concept of inverse clearer. And now we shall see a proposition with regard to inverse functions. Now, f is a function from a to b, and let us say the inverse exists and we have f inverse. Then if it the purpose or the guarantee that f inverse exists lies on the fact that f is 1 1 and onto. Now, this might seem quite obvious, because if we can see this example, imagine this is a 1 1 and onto function. If it weren't 1 1 or onto, what would happen when we find the inverse function? It would cease to be a function at all. It would cease to be a function. For example, if a and b were not 1 1 and onto, then there might be a function, let us say, there could be elements that are mapped like this. Now, what would be, if this is f going from a to b, then what would be f inverse? F inverse of this element, say if this is x and let us say this is 1, 2 and 3, what would be F inverse in this case? It would be 3 elements. So, F inverse of x would mean that it has 3 images, namely 1, 2 and 3, which would make it invalid as a function. So, it is obvious that the proposition requires that f should be 1, 1 and onto for a function to have inverse. So, from the example it is obvious, but let us now find the mathematical proof. Now, proof is, suppose let us assume for example f is 1, 1 and onto. Then it means that for any b belonging to the codomain B, there exists one element A inside A such that f of A is equal to B. Since f is 1, 1 and onto, this is true. Alright. So, and this means that the ordered pair, this f of A equal to B is represented as an ordered pair A comma B belonging to F, which means that f inverse is equal to B comma A, or f inverse of B is equal to A. If f of A is equal to B, obviously f inverse of B is going to be A for every ordered pair A comma B belonging to the set, belonging to the function f. So, it is quite obvious that if f is 1, 1 and onto, it is going to have a inverse function. Let us see the converse. Now, this is an if and only if condition, as necessary and sufficient condition. So, I have to prove the reverse as well. So, suppose I have a function which has an inverse, then I must prove that f is 1, 1 and onto. Converse, suppose f inverse exists from B to A, and now I must prove that it is onto, and then I am going to prove that it is 1, 1. So, if it is onto, given any B belonging to B from so for f inverse, this is the domain and A is the codomain. So, for every B belonging to B, there exists some A comma B belongs to F, obviously, and so this is true. And for 1, 1, if you recall, we always try to find, in order to check for 1, 1, we always check whether if I take 2 images which are equal, are the elements themselves equal. So, if f of A1 is equal to f of A2, imagine, let us say for example, if these 2 elements, obviously they do not have, if it is not the same here, but still imagine if 1 is equal to 2 here, it means that these pre-images should also be equal. That happens only if it is 1, 1. If it weren't 1, 1, what will happen is that you will get f of A1 equal to f of A2 means that A1 not equal to A2. So, you can check for that, but this is the usual procedure for checking for 1, 1. So, f of A1 equal to f of A2, A1 comma A2 belongs to A means let that be some image. So, since this is going to be in B, so f of A1 equal to f of A2, which is going to be in B, because f is from A to B. So, this will be B. So, A comma B belongs to F, and A1 comma B belongs to F, and A2 comma B belongs to F, means that B comma A belongs to F inverse and B comma A2 belongs to F inverse. Why is that? Because we have said that F inverse exists. So, if F inverse exists, for every pair in F, you have another pair in F inverse. So, because of that, this is true. But this is a contradiction to the fact that f inverse is a function, it is an inverse function. So, as we were seeing, let f of A1 equal to f of A2 is B. So, I am taking 2 elements which are same and they are having the same value, which is B, and A1 comma B belongs to F and A2 comma B belongs to F. So, this means that f of A1 is mapped to B and f of A2 is mapped to B, that is all. And which means, since we have said that f inverse exists for every term in A comma B belonging to F, this means that B comma A1 belongs to F inverse and B comma A2 also belongs to F inverse. Now, this is a contradiction. Why? Because, can you see this example? It will lead to a situation where if I find the inverse of x, it means that it is having 3 values. X is mapped onto 3 values for F inverse. Of course, while going from A to B, it might make sense, but when I am going from F inverse, it will not make sense. This is the same situation that will happen here also. So, A1 is also mapped onto B and A2 is also mapped onto B, which means that this is not a function. So, this is a contradiction to f inverse being a function. which means that the only way this can happen is if A1 is equal to A2. So, whenever f of A1 is equal to f of A2, I have proved that A1 is equal to A2, which means I have proved 1 1, I have proved onto, and hence the theorem is done. So, I have proved both sides of the theorem. Next, a small note to remember here, if g is a function such that xy belongs to g, if and only if g of x is equal to y, that is if b of b comma a belongs to f inverse, if and only if a is equal to f inverse of b. So, this means that a comma b belongs to f, which means that f of a is equal to b. So, if you are introducing a g function, again the same definitions hold. Now, we shall see an example. Let us consider a real valued functions, and let us say it is from R to R itself. So, here also it is going from the domain is also the set of real numbers, the codomain is also the set of real numbers, and I am defining the function f of x to be 3x plus 5. And I have to prove that it is 1 1 and onto, and I am going to check for f inverse. And so, f y is equal to f inverse of x implies that x is equal to f of y. Obviously, if f inverse exists, this should be quite valid. Hence, f of y should be equal to 3y plus 5. So, what I am doing is merely substituting, instead of x I am substituting y. So, f of y is equal to 3y plus 5. But what do we know about f of y? It is equal to x according to this. So, x is equal to 3y plus 5. So, y in terms of x should be written as, just bring 5 to the left hand side. So, x minus 5 is equal to 3y you will get. So, y is equal to 1 by 3 x minus 5. So, if f of y is equal to x, then y is equal to 1 by 3 x minus 5 should be f inverse of x. Why? Because y is f inverse of x. So, instead of y I have merely substituted f inverse of x, and this will be the inverse function. So, for 1 1 and onto, you can, it is quite obvious from the previous theorem that f inverse exists, it is 1 1 and onto. If it is 1 1 and onto, f inverse will exist. So, I have proved that inverse exists, which means that it is going to be 1 1 and onto. No need to prove at all if we are just going to use the previous theorem. Next, we will see another example. Let us say I have a function of real numbers from the real number system except 1, and the codomain is a set of real numbers except 3. Why am I restricting these sets like this? Is because we have trouble here. So, whenever the denominator is 1, what will happen to function f of x? It will collapse, it becomes an indeterminate function. So, I am restricting my values to r minus 1 and here r minus 3, and here f of x is from f of x is defined to be 3x plus 2 by x minus 1. Now, what is f inverse of x? It would be some y, it would be some y, and that is what I have written here. So, y, if I were to substitute y, f of x is equal to y. So, f inverse of x is equal to, so y is equal to 3x plus 2 by x minus 1, which means that x is equal to 3y plus 2 by y minus 1, right. So, wherever there is x, I am just inverting it. So, wherever there is x, just substitute y, and wherever there is y, I am substituting x. Now, you solve in terms of x. So, x into y minus 1 is equal to 3y plus 2. So, xy minus x is equal to 3y plus 2. So, xy, bring the y to the one side. So, xy minus 3y is equal to x plus 2, and I get y is equal to, take x y common here, you will get x minus 3 and y equal to x plus 2 by x minus 3, and this will be your f inverse of x. Why? Because f inverse of x is equal to y. So, this is your inverse function. So, given one function, how to find the inverse function? So, this is the technique behind it, and now this particular part will make sense. Why am I restricting r to r minus 3? Because denominator here, if I put 3, f inverse of x will collapse and become an indeterminate function. So, that is why I have restricted even the codomain to r minus 3. Now, we will see one more proposition. F from A to B is 1 1 and on to, implies that f inverse from B to A is also 1 1 and on to. We should not confuse this with the previous theorem, which says that the conditions were given only for f. if f is 1 1 and onto, f inverse exists, and if f inverse exists, f is 1 1 and onto. This theorem is different. It says that if f is 1 1 and onto, f inverse is also 1 1 and onto. So, we shall check. So, I need to check for 1 1 and onto-ness. So, whether it is bijective, that is what I am going to check. Let us take the function f inverse of b1 equal to f inverse of b2. Like I said, this 1 1 1, if I whenever I am checking for 1 1-ness, I need to go by taking two images as equal elements, which means that f inverse of b1 should be some a1, because f inverse b from b to a. So, naturally f inverse of b1 would yield a term inside a, so that is a1. a1 is equal to f inverse of b1 and a2 is equal to f inverse of b2. So, we have, suppose if a1 is equal to a2, it means that b1 is equal to f of a1 and f of a2 is equal to b2. So, thereby proving my condition that f inverse of b1 equal to f inverse of b2 means that b1 is equal to b2. Okay. We shall see the proof of this theorem. So, I need to prove that f inverse is also 1 1 and onto. So, for that I like the usual technique. So, f inverse of b1 is equal to f inverse of b2, and I must prove that b1 is equal to b2, only then I can say f inverse is 1 1. So, we know that because f inverse is from b to a, naturally f inverse of b1 should be an element inside a, therefore, a1 is equal to f inverse of b1 and a2 should be equal to f inverse of some a2 is equal to this f inverse of b2. Now, why we have a1 is equal to a2? Why is that? Because f is 1 1 and onto. Hence, a1 should be equal to, because f is 1 1 and onto, f of a1 equal to f of a2 would mean that a1 is equal to a2. Therefore, since a1 is equal to a2, this means that f of a1, b1 will also be f of a1, and can you see? So, a1 equal to a2 would mean that taking this to the other side, it would become f of a1 equal to b1, f of a2 equal to b2. So, b1 equal to b2 is what I have proved using the condition that f is 1 1 and also these two things that we have already seen. So, together I am able to prove that b1 is equal to b2, and hence I proved that f inverse is 1 1. The onto-ness is quite easy. If I take any a belonging to a being this set, then f of a is equal to b belonging to b. Why is that? Because f of a is onto, which means that every element in b is having a pre-image in a. So, going by that argument, a belonging to a, f of a equal to b would belong to b. Just reverse this function to the other side. So, you would get a is equal to f inverse of b for every a belonging to a. This means that f inverse is also onto. Now, composition of functions. Now, this is so long we have been seeing about the inverse of a function. Now, we shall see about composition of functions. It is an important kind of binary operation that we will study, and something that will constantly appear in the upcoming courses also. So, pay attention. So, f is a function from a to b, g is a function from b to c, implies that g composition f. So, g composition f, it always goes like this, is from a to c. So, if I go like this from a to b, b to c and not c to a. So, when I put g composition f, it is actually a to c, whereas f composition g would go in the opposite side. So, g composition f is from a to c and it is given by g composition f of a is g of f of a for all a belonging to a. So, merely a sort of an off function is happening, and for this it is best explained with the help of an example. So, I am going to use this example. Let us imagine f and g to be functions from R to R, the set of real numbers, and f of x is defined as 3x minus 1 and g of x is defined to be x squared plus 2. Now, g composition f of x is from a to c. So, since it is all R, there is no worries there from where to where it goes, it is going to be the same anyway. G of f of x which means that I substitute f of x first. So, g of 3x minus 1, and wherever, which means that whenever I substitute x, I am getting x squared plus 2. So, instead of x, I am having 3x minus 1 here. So, instead of x squared, wherever I have x, I have to substitute 3x minus 1. So, 3x minus 1 the whole squared plus 2. So, and this will yield an answer. Obviously, I have not expanded it, but that can be left an exercise to the learners. F composition g of x will go from C to A, and again it does not make any difference here since it is all R to R. And here f of g of x would be, so instead of g of x, substitute this value x squared plus 2. So, f of x squared plus 2 would yield 2 into, and now what do we know about f of x? It is 3 times x minus 1. So, this should be 3 into x squared plus 2. So, f of g of x is f of x squared plus 2. I have just substituted this term here. So, 3 times, instead of x, I have x squared plus 2 here. I just plug in that value here. So, 3 into x squared plus 2 minus 1. You can expand and see and get the answers for f of g of x and g of f of x. So, this is how you do composition of functions. Next, we shall see about equality of functions. Functions f and g are equal if and only if they have the same domain, same target, and f of a is equal to g of a for every a in the common domain. We shall see a proposition. Composition of functions is an associative operation. Proof: we must prove that f composition g composition h is equal to f composition g composition h whenever each of the two functions f composition g composition h and f composition g composition h is defined. Thus, we assume that for certain sets a, b, c and d, h is a function a to b, g is a function from b to c and f is a function from c to d. Since the domain of f composition g composition h is the domain of f composition g composition h, namely the set A. We have only to prove that f composition g composition h of the element A is equal to f composition of g composition of h of the element A for any A belonging to A. For this, we have f composition g composition h of A is equal to f composition g of h of A, f of g of h of A, and f composition g composition h of A is equal to f of g composition h of A into f of g composition h of A as desired. Proposition: functions f from a to b and g from b to a are inverses if and only if g composition f is equal to I A and f composition g is equal to I B. That is, if and only if g of f of A is equal to A and f of g of B is equal to B, for all A belonging to A and for all B belonging to B. We shall see the proof. If f from A to B has an inverse f from B to A, then we have already seen that f inverse of B is equal to A if and only if B is equal to f of A. So, for any A belonging to A is equal to f inverse of B, which is equal to f inverse of f of A, which is equal to f inverse composition f of A. In other words, the composition f inverse composition f is equal to IA, the identity function on A. Similarly, for any element B belonging to B, B is equal to f of A is equal to f of f inverse of B, which is equal to f composition f inverse of B. Thus, the composition f composition f inverse is equal to IB is the identity function on B. In this session, we have learnt about the concept of inverse of a function, composition of a function and equality of a function. We have also got to know how to find the inverse of a function. Numerous results linked to these specific topics were studied in detail. I hope that this was of use to you, and there are further examples if you are interested in the script. Do try them out. Thank you.